Hello everyone, and welcome to our video on applications of double integrals. So, definition, a two-dimensional closed surface with mass and density is called a planar lamina. So think of this like a thin plate. So suppose a lamina occupies a region D of the xy plane, and its density at a point xy and D is given by rho of xy, where rho is a continuous function on D, then rho of xy equals the limit of delta m over delta A, where delta m and delta A are the mass and area of a small rectangle that contains xy, and the limit is taken as the dimensions of the rectangle approach 0. So, of course, density in general, we think of if density is continuous, or is, is the same, homogeneous, right? If the density is the same across the whole mass, you would just say, well, take the mass and divide it by the area. That's your density. But in this case, we're saying, well, it's not necessarily the same. But if you have a rectangle around your point, and you go, well, what's the mass of this divided by its area? And then you take smaller and smaller rectangles, you're going to get the density, right? So each one of those is going to give you an approximation of the density at the point. And then as you take that limit, you're going to get the exact density at that point. So we can construct a Riemann sum as usual and approximate the total mass of the lamina by taking a double sum of the density times the area of each corresponding rectangle. So the density at a point times the area of the rectangle that contains that point. So again, this kind of double sum is like if you divide it into a bunch of columns and rows on your region, and you took all of the rectangles in one column or one row, and then that's one sum inside, and then you move to I equals 2, and then the sum inside becomes the next row. And then I equals 3 makes you sum this row, so forth and so on. So this leads naturally to the formula that mass equals the double integral of the density at x and y with respect to area. So other types of density can be treated in the same way. So if this omega xy gives the charge density in units of charge per area, then the total charge is given by Q equals the density function at xy dA. All right, so let's move on to an example here. Electrical charge is distributed over the disk, x squared plus y squared is less than or equal to 1, so that the charge density at xy is the square root of x squared plus y squared. Find the total charge on the disk. Okay, so the total charge is just going to be given by the double integral over the region of the square root of x squared plus y squared dA. Now, the thing is, when we think about this region, the region is over a disk, and we've got this x squared plus y squared in here. So those are kind of two big hints that this problem is probably easier to solve if we put things in polar coordinates. So this region, as we've seen in polar coordinates, can be described by a radius between 0 and 1 and theta between 0 and 2 pi. So that allows us to convert this equation into an integral from 0 to 2 pi and 0 to 1 of, now we replace x with r cosine of theta, and we square it. Replace y with r sine of theta and square that. And then this becomes r dr d theta. Okay, Inside here, we get r squared cosine squared plus r squared sine squared. We take the r squared and factor it out, times cosine squared plus sine squared, which is 1. So we get left with the square root of r squared times r. Well, that's just r times r, which is r squared. So hopefully that wasn't too much to skip, but we've done that kind of manipulation a few times now, so hopefully it won't be a problem. Now, if I integrate this with respect to r, we get r cubed over 3 evaluated from 0 to 1 d theta. This is going to be 1/3 minus 0 d theta. That's theta over 3 evaluated from 0 to 2 pi, which gives us just 2 pi thirds. So that's the total charge on the disk. Okay, so let's look at this idea of moments and centers of mass. Okay, so the moment of the lamina about the x-axis is m sub x equals the double integral of y times rho of xy dx. So if you want to see a more thorough treatment of sort of the background of this, I have a video on applications to physics and engineering in my Calculus 2 playlist. But the general gist is this. So again, since I've already kind of covered that stuff in another video, I'm not going to go super in detail. But here's your point. You've got this point 0, 0. And I'm not a physicist, so my explanation may be a little bit poor, my layman's explanation. But if we think of any point along this lamina, that point is a distance of y from the x-axis. And so when you combine that y times the density at that region, it sort of suggests how much that point is contributing to sort of twisting or weighing down the mass in that direction. So when you take this double integral, remember these are really double sums. What you're saying is you're taking the sums of the distance away from the axis, the x-axis, times the density at that point. You're adding all those sums together. So you're essentially saying, okay, how much is this mass being pushed in a specific direction, up away from the x-axis? And similarly, the moment about the y-axis, m sub y, is the double integral of x times the density function with respect to area. So the center of mass is given by x bar being the x-coordinate, the moment about the y-axis divided by the mass of the lamina. So remember, these moments are sort of describing the amount that the mass of at each point is contributing to weighing this thing in a given direction. And so if we divide that by the total mass, what we get is the coordinate that is essentially the balancing point. So the way you think of this center of mass, or the way I think of it at least, is that this x bar, y bar is the point at which, well, that definitely wouldn't be the point. So let me draw it somewhere kind of realistic. Maybe it's about like here. X bar, y bar. So this is the point at which you imagine if you balanced this thin plate on top of like a spike, right? Just a tiny point. You could balance it right on that point and it wouldn't tip over. So that's the center of mass. So you find the x-coordinate by taking the moment about the y-axis and divide it by the mass, which we can rewrite in this form. And you find the center of the y-coordinate for the center of mass by taking the moment about the x-axis and divide it by m. Again, remember, the moment about the x-axis is talking about the distance from the x-axis, which is a y value. And likewise, the moment about the y-axis is talking about the distance from the y-axis, which is an x value. So these give you your formulas for your coordinates with the fact that the mass is given by the double integral of the density function with respect to A. All right, so with that said, let's take a look at an example. Find the mass and center of mass of the lamina that occupies the region D and has the given density function P. Okay, so here we've got to make use of all of these density formulas that we've got. So first we need to know what the mass is, and then once we know that, we can calculate the center of mass. And so let's just go ahead and start by finding the mass. So the mass is just the double integral over the region of the density function. Okay, and what do we have here? We have x goes from 0 to a, and y goes from 0 to b. So we could really choose whichever way we want to set this up. So how about we'll integrate with respect to x first? Doesn't make much difference here. And then y. So integrating with respect to x gives us x plus x cubed over 3 plus y squared x, evaluated from 0 to a, dy. Okay, now when we evaluate this at a, what do we get? We get a plus a cubed over 3 plus y squared times a. And when we evaluate at 0, all of those terms disappear, so we don't have to worry about that. Now we integrate with respect to y, we get a plus a cubed over 3. Those are both constants, so when we integrate them together, we'll get the constants times y, plus y cubed over 3 times a, evaluated from 0 to b. This gives us a plus a cubed over 3 times b plus b cubed times a over 3. And when we evaluate at 0, we'll get 0. So don't have to worry about that either. Now, I can make this 3a over 3. So that lets me combine this all together into one fraction. 3a times b, if I distribute the b, plus ba cubed plus b cubed a all over 3. So I'll just leave that in that form for now. I could factor both an a and b out of this term, but I don't know that would help me all that much right now, so let's just go ahead and move on. Okay, so now that we have m, we would like to evaluate what x bar is. So, but in order to evaluate x bar, I need the moment about y. And how did we get the moment about y? Well, it's the same double integral, and we use the same density function, but for the moment about y, we're looking at the density, or the density function rho times x for the moment about the y-axis. So right here. So we just multiply x times our function, 1 plus x squared plus y squared. And this is going to be very much the same kind of integral. So again, not a super fun computation to make, but sometimes we have to deal with some crazy computations. So x plus x cubed plus y squared x is what we get inside this integral. Our bounds are the same from 0 to a and 0 to b. And we're integrating dx dy again. Okay, so let's go ahead and knock that out. Integrate with respect to x first, get x squared over 2 plus x to the 4th over 4 plus y squared x squared over 2. Evaluate that from 0 to a. And remember, you're evaluating at x here, so this becomes a squared over 2 plus a to the 4th over 4 plus a squared x, a squared y squared over 2. And then when we evaluate 0, that's all just going to disappear. Okay, so we can integrate this with respect to y. I could have combined these constants like I did for the mass problem, but it doesn't make a difference in the end. So let's just integrate these with respect to y. We get a squared over 2 times y plus a to the 4th over 4 times y plus a squared times y cubed. I need to divide by 3, but there's already a 2 there, so that becomes 6. And now we need to evaluate this from 0 to b. So this becomes a squared b over 2 plus a to the 4th times b over 4 plus a squared b cubed over 6. And when we evaluate at 0, those are all going to be 0. So let's just find a common denominator here. So we need a factor of 12 in our denominator. So 6a squared b plus 3a to the 4th b plus 2a squared b cubed all over 12. Again, don't know if that's going to make a big difference, but it certainly won't hurt. So we'll go ahead and write that out that way. And now we just need to go ahead and compute our moment about x. So that's going to be this same kind of double integral, but it's going to be y times the density function. Okay, so when we multiply y times this density function, what do we get? We get y plus yx squared plus y cubed. And we'll integrate with respect to x, then y. So this gives me xy plus y times x cubed over 3 plus y cubed times x, evaluated from 0 to a. And now we evaluate this as x equals a and x equals 0. So what does that give us? That gives us ay plus a cubed y over 3 plus a times y cubed. When we evaluate at 0, all the terms disappear. Very convenient. Now we'll integrate with respect to y, and we get ay squared over 2 plus a cubed y squared over 3 times 2, which is 6, plus a y to the 4th over 4, evaluated from 0 to b. That's going to give us ab squared over 2 plus a cubed b squared over 6 plus ab to the 4th over 4 minus 0. And so now I just need a common denominator again. That'll be 12, so I get 6ab squared plus 2a cubed b squared plus 3ab to the 4th, all over 12. So now I've got everything I need. I have my moment about the x-axis, my moment about the y-axis, and I have my mass. So now if I want to find the center of mass of the lamina that occupies this region, all I got to do is divide my moments about my mass. So x bar is the moment about the y-axis divided by the mass. So that's 6a squared b plus 3a to the 4th b plus 2a squared b cubed over 12. And instead of dividing by the mass, I'm going to multiply by its reciprocal. So that's 3 over. And what did we have there? 3ab plus ba cubed. 3ab plus ba cubed plus b cubed a. So 3 over 12 becomes 1/4. And now I'm going to see if I can factor out some common terms here just to simplify this down a little. So I've got an a squared in each of these terms and a b. So I can factor out a squared b. And what do I get left? 6 plus 3a squared plus 2b squared. Divided by, and here we've already got this 4 times. Now out of here we can factor out an a and a b. And this leaves us with 3 plus a squared plus b squared. So that allows me to cancel one of these a's and this b. I get left with a over 4 times 6 plus a squared plus 2b squared, 3a squared plus 2b squared over 3 plus a squared plus b squared. So if only we knew what a and b were, we could evaluate this precisely, but this at least gives us a relatively simple formula for finding that center of mass. Okay, now y bar is going to be the moment about x divided by m. Okay, so this is going to be 6ab squared plus 2a cubed b squared plus 3ab to the 4th over 12 times the reciprocal of the mass again, 3 over 12 is 1/4. Now up here we can factor out an a and a b squared. This leaves us with 6 plus 2 times a squared plus 3 times b squared divided by 4 times. Now here we can factor out an a and a b. And we get left with 3 plus a squared plus b squared. And finally, cancel an a and one of the b's, we get b over 4 times 6 plus 2a squared plus 3b squared over 3 plus a squared plus b squared. Okay, and that's it for that problem. It's a little bit of a doozy. So some of these problems are pretty time consuming. There's not much way around it. I wish there was some good shortcuts, but sometimes you just got to work them through. All right, so let's move on to this next example. The density at any point on a semicircular lamina is proportional to the distance from the center of the circle. So, of course, we can always center our circle, since it's not specified, at 0, 0. That's going to be the easiest thing to do. So the density at any point on a semicircular lamina, so this is going to have radius r, and it's going to be half of a circle. Now, the density is proportional. That means it's a constant multiple of the distance from the point to the center of the circle, which is just x squared plus y squared's square root. So it says find the center of mass of the lamina. Okay, well, the first thing is, since this is proportional to the distance from here, and we have this symmetry along the y-axis, the basic geometry of this problem says, hey, you're going to have the same mass on each side here, so the y-bar coordinate has to be 0. That's only because you have this symmetry on the y-axis. Now, we don't have that because we're not symmetric over the x-axis. We're just looking at a semicircle here. So we can at least take that for y-bar, and that does save us a little bit of time. Okay, so now what? Well, what we would like to do is take the moment about, so if this is y-bar, that's the moment about x divided by the mass. So I need x bar, which is the moment about the y-axis divided by the mass. So that means I need to calculate the mass and the moment. So the mass would be the integral over the region of k times this square root. And this should really look like, hey, you've got a semicircle here, and you've got this x squared plus y squared polar coordinates. Got to do the polar coordinates here. So let's take a look. How does this region get described in polar coordinates? It would be r is between, actually, let's call these cap r for the radius of our circle, and little r will be our variable. So our little r here has to be between this cap r and 0. And then any angle between 0 and pi. So, first of all, k is a constant, so I can pull it out in front. This will be the integral from 0 to pi, and 0 to cap r. And then inside this square root, what do we get? We get r cosine of theta squared plus r sine of theta squared. R times dr times d theta. So this is k times the double integral. And here, again, we get r squared cosine squared plus r squared sine squared. We factor out the r squared. That's r squared times cosine squared plus sine squared, which is 1. And the square root of r squared is r. Times r is r squared. So we've seen this a few times now, so hopefully it's okay that I'm skipping a little bit of that. So this becomes this integral, r squared dr d theta, which is pretty straightforward to integrate. So we get the k times the integral from 0 to pi of r cubed over 3, evaluated from 0 to cap r, d theta. Evaluate this at the endpoints here, we get cap r cubed over 3 minus 0 d theta. Now we integrate this with respect to theta. We get k r cubed over 3 times theta evaluated from 0 to pi. And finally, that gives us, I'll write this r cubed times k theta, or times k pi over 3. So there is our mass. Now let's evaluate our moment about y. Just remember when we say moment about the y-axis, the distance away from the y-axis is x. So we're multiplying this by our density function, which was k times the square root. I'm going to pull k out in front again. Now again, for the sake of time here, I'm going to try to skip a little. X is r times cosine of theta. And then inside this square root, I would have ended up with the square root of r squared when I do my substitution just like before, which is r times r d theta. So altogether, this gives us r cubed times cosine of theta. So if I integrate this with respect to r, I get the integral from 0 to pi of r to the 4th cosine of theta over 4, evaluated from 0 to cap r, d theta, which becomes cap r to the 4th power cosine of theta over 4. And when we evaluate at 0, we just get 0. And d theta. Now the integral of cosine of theta is sine of theta, so this becomes r to the 4th sine of theta over 4, evaluated from 0 to pi. What am I doing here? Oh, okay. I did something very silly, but that's all right. Here we go. X bar is 0 because the x coordinate is 0 on the y-axis. So I flipped those around. That should have been x bar is 0. And y bar should be the moment about x divided by m. So I actually needed the moment about x here, which changes this integral quite a bit. So gotta watch out for those little things. And this is how you know these videos are not scripted. Real, live mathematics. So y is going to be r times sine of theta. And that makes this sine of theta. So when we integrate that sine of theta, let's see, that should still be sine of theta here because we integrated with respect to r. And here, when we integrate sine of theta, we should get negative cosine of theta. Cosine of pi is -1, so a negative -1 becomes positive r to the 4th over 4, minus, and then evaluated at 0. So cosine of 0 is 1, so that's going to be minus a negative r to the 4th over 4. So that's 1/4 of r to the 4th plus 1/4 of r to the 4th. That's r to the 4th over 2. And I dropped k. A nice extra mistake here. So there should be a k there. Okay, that's it for mistakes on this one. So mx is equal to k times r to the fourth over 2. So therefore, y bar is the moment about the x-axis divided by the mass, which is k r to the fourth divided by 2 divided by r cubed times k times pi over 3. Okay, k over k cancels. R to the fourth over r cubed is r, so this is 3r divided by 2 pi. And that's it. That's y bar. So the center of mass x bar y bar is 0, 3r over 2 pi. Definitely watch out for those little mistakes because, hey, if I'm making them fairly often, anybody can make. Which isn't to say I'm special. It's just to say that it happens to the best of us and the middlest of us. That would be me. All right. What's up next? So let's take a look at one more idea here. The moment of inertia. So this describes essentially a body's tendency to resist angular acceleration. So the moment of inertia about the x-axis is given by I sub x equals the double integral of y squared times the density function. And the moment of inertia about the y-axis is given by I sub y, which equals the double integral of x squared times the density function with respect to a. And then the moment of inertia about the origin, also known as the polar moment of inertia, is given by the double integral over the region of x squared plus y squared times the density function. So notice that the moment of inertia about the origin is the sum of these previous two moments. So let's go ahead and tackle this one. Find the moments of inertia of a homogeneous disk D with density rho, center at the origin, and radius a. So in other words, the density is a constant value here. So if we take a look at this region, so the center is at 0, 0. And what would our integral look like for our moment of inertia? All right, so for the moment of inertia about the x-axis, that's going to be the double integral over d, y squared times rho with respect to a. Now, it might not be obvious at first glance, but if we try to do this in Cartesian coordinates, you've got to have an upper bound and a lower bound for y that are going to look like square roots of a squared minus x squared and negative the square root of a squared minus x squared. And so this integral is going to become very complicated very quickly. But if we realize we can easily describe this region with polar notation, we can say, well, r here is just between 0 and a, and theta is between 0 and 2 pi. And once again, polar coordinates can save us quite a bit of effort. So let's convert this to polar coordinates, or a polar integral, I should say. 0 to 2 pi, 0 to a. Y squared is going to become r squared sine squared of theta. And rho, again, is a constant. And then we've got r times dr d theta. So I can pull rho out in front, and then this becomes r cubed sine squared of theta dr d theta. Now we integrate with respect to r. We get r to the 4th over 4 times sine squared of theta, evaluated from 0 to a, and then we'll integrate again with respect to theta. This becomes rho times the integral from 0 to 2 pi of, okay, so we're evaluating r here. So this becomes a to the 4th over 4 times sine squared of theta. And then when we evaluate at 0, we get 0. Now a is going to be a constant, so we can pull out this rho times a to the 4th over 4 times the integral from 0 to 2 pi of, now we've got sine squared of theta here, but we'll want to use our power reducing formula, which should give us 1 minus cosine of 2 theta all over 2. So if I pull that 1/2 out, I get rho a to the 4th over 8, and then I integrate 1, and I get theta, and integrate cosine, I get sine of 2 theta divided by 2. And now we want to evaluate this all from 0 to 2 pi. Well, if I plug in 2 pi here, I get rho a to the 4th over 8 times 2 pi minus sine of 4 pi, which is 0. And then when I plug in 0, I get 0 for both of these. So this is it. So this is pi times rho times a to the 4th over 4. Now, I'm going to go ahead and evaluate the moment of inertia about the origin next. And I'm going to do that because I see this x squared plus y squared, and I think in polar form, that might be a little bit easier. So, about the origin, we get the integral over d of x squared plus y squared times rho of xy, but in this case, rho is just a constant, so I'll just leave it like that, dA. So if we convert this, what do we get? We get r squared cosine squared of theta plus r squared sine squared of theta times rho times r dr d theta. Well, again, factor out the r squared. You get cosine squared plus sine squared, which is 1, times r gives us r cubed. And I'll pull the constant rho out in front. So inside we just have r cubed dr d theta, and evaluated from 0 to a, and 0 to 2 pi here. So this is rho times the integral from 0 to 2 pi of r to the 4th over 4, evaluated from 0 to a, d theta. This is going to be a to the 4th over 4 d theta. Evaluating at 0 just gives you 0. And now when I evaluate this, I get rho a to the 4th over 4 times theta from 0 to 2 pi. So I'm just going to get 2 pi, and then over 4, the 2 is going to cancel. So I get rho a to the 4th times pi over 2. Now notice that about the origin, this is equal to about each axis summed together. And I already have the moment, or the moment of inertia about the x-axis. So I can find the moment of inertia about the y-axis by just noting that it is the difference of these two. Rho a to the 4th times pi over 2 minus rho a to the 4th times pi over 4, which leaves me with 1/4 of rho a to the 4th pi. All right, so that's it for this moment of inertia about the origin. Okay, so we got like one more subtopic here to tackle. Thought I would need more room, so, I left all this extra space there. But that's okay. The radius of gyration of a lamina about an axis is the number r such that m times r squared equals I, where m is the mass of the lamina and I is the moment of inertia about the given axis. So, this effectively states that if the mass of the lamina were concentrated at a distance of r from the axis, then the moment of inertia at this point of mass would be the same as the moment of inertia of the lamina. In particular, the radius of gyration with respect to the y double bar with respect to the x-axis and the radius of gyration y x double bar with respect to the x-axis are given by m y double bar squared equals I sub x and m x double bar squared equals I sub y. Thus, the coordinate x double bar y double bar is the point at which the mass of the lamina can be concentrated without changing the moments of inertia with respect to the coordinate axes. That's a lot to say, but you just think of like if you took all the mass of the lamina and you put it in one point, then it doesn't change the moments of inertia, right? That's about the summary right there. Okay, so example. Find the radius of gyration about the x-axis of a homogeneous disk D with density that's constant, center at the origin, and radius A. Okay, so the first thing to realize is that this problem is pretty similar to the problem that we were looking at before in example 4. So first, well, let's just figure out what do we need here. We need the mass. So that's m. We need the mass. Let's just calculate that mass. So what's the mass? Well, it's this double integral with respect to, or of rho times dA. And what's that going to give us? Well, when we convert this into polar coordinates like we had before, we've got 0 to a and 0 to 2 pi. And this is rho times r dr d theta. So this becomes r squared over 2, evaluated from 0 to a, d theta. And now I'll pull the rho out in front. So this becomes a squared over 2, d theta. And so this is rho a squared over 2 times theta, evaluated from 0 to 2 pi. And so this becomes pi times rho a squared. So that's the mass. Okay, well that's the mass. What else do we need to know? We need to know the moment about the x-axis and the moment about the y-axis. But that's okay because we already did that, right? So what's our moment about the x-axis? We'll just copy this. Okay, pi times rho times a to the 4th. Okay, so then what does this tell us? Well, we know that the mass times y double bar squared is equal to this moment of inertia. So that implies pi times rho a squared times y double bar squared equals pi times rho a to the 4th over 4. So the pi's cancel, the rho's cancel, and then a to the 4th will become a squared when I divide that out. And so if I take the square root I get y double bar equals a over 4. Or a over 2, I should say. All right. Now that we've got that, what else do we need? Well, we need x double bar. And technically, I should have plus or minus here. So for y double bar, that should be plus or minus a squared over 2. A squared over 4's square root, so plus or minus a over 2. Now we know that x double bar squared is equal to the moment of inertia about the y-axis. Okay, so what did we have for that? Well, we've still got the same mass, so that's pi rho a squared equals, or times x double bar squared equals the moment about the y-axis, but we found that that was the same exact value, right? So here, this is the same value that we had for x, so that makes things a little bit easier. What does that tell us? That tells us x double bar squared is going to also be equal to a squared over 4, which tells us x double bar is plus or minus a over 2. But I guess I should point out that since the radius of gyration is exactly that, a radius, we actually don't need the plus or minus because that's just meant to be a distance. So, in other words, the distance, the radius of gyration is a over 2 for both the y-axis and the x-axis. All right, well, that's it for 12.4, applications of double integrals. Thanks for sticking around. Have a great day.